What if the universe is expanding faster than we can comprehend, and the answers to its greatest mysteries are slipping further out of reach? Imagine standing at the edge of the cosmos, staring into an endless expanse where galaxies drift apart like leaves on a cosmic river. Yet, despite all our advancements, the universe holds secrets that even the brightest minds cannot unravel. Today, we dive into 25 unsolved questions about the universe's expansion, mysteries that continue to baffle scientists and challenge our understanding of reality. From the enigmatic force of dark energy to the ultimate fate of the cosmos, these questions remind us just how much we have yet to discover. So, are you ready to explore the unknown? Stay with us, because by the end of this journey, you'll see the universe in a whole new light, and you might just find yourself questioning everything you thought you knew. Let's begin. Now, turning to the first of our 25 unsolved questions, we encounter one of the most perplexing mysteries in modern cosmology. What is dark energy? This mysterious force is believed to be the driving factor behind the universe's accelerated expansion, a discovery that shook the foundations of physics when it was first confirmed in the late 1990s. Scientists observed that distant supernovae were fainter than expected, suggesting that the universe wasn't just expanding, it was doing so at an ever-increasing rate. But what exactly is causing this acceleration? That's where dark energy comes in. Current theories suggest that dark energy makes up roughly 68% of the universe's total energy content, yet its true nature remains elusive. Some propose it could be a property of space itself, often referred to as the cosmological constant, a concept introduced by Albert Einstein and later abandoned, only to resurface as a potential explanation for this cosmic phenomenon. Others speculate that dark energy might be a dynamic field, changing over time and interacting with the fabric of the universe in ways we don't yet understand. Despite decades of research, dark energy has never been directly observed, and its existence is inferred solely through its effects on the cosmos. This makes it one of the greatest enigmas in science, a puzzle that challenges our understanding of physics and the very nature of reality. Why does dark energy dominate the universe? How does it interact with matter and space? And could it hold the key to understanding the ultimate fate of the cosmos? These are just some of the questions that keep scientists awake at night. And as we continue our journey, we'll explore how this mysterious force shapes the universe we live in. Now, turning to the second of our 25 unsolved questions, we delve into another cosmic mystery. Why is the universe expanding faster than expected? This puzzling discrepancy, known as the Hubble tension, has become one of the most hotly debated topics in modern cosmology. It all began when scientists tried to measure the rate at which the universe is expanding, a value known as the Hubble constant. Using two primary methods, observing distant supernova and analyzing the cosmic microwave background, researchers expected to arrive at the same number. But instead, they found a significant mismatch. The cosmic microwave background, the afterglow of the Big Bang, suggests a slower expansion rate, while observations of supernova and other nearby celestial objects indicate a faster one. This inconsistency has left scientists scratching their heads, as it challenges our understanding of the universe's fundamental properties. Could there be an error in our measurements, or is this tension pointing to something deeper, perhaps a flaw in our current models of physics? Some researchers speculate that the Hubble tension might be hinting at the existence of new physics, such as an unknown form of dark energy or even modifications to Einstein's theory of general relativity. Others suggest that the discrepancy could be due to unaccounted-for factors in our observations, like the distribution of matter in the universe or the behavior of dark matter. Efforts to resolve this puzzle are ongoing, with new telescopes and advanced technologies being developed to refine our measurements. Missions like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope aim to provide more precise data, potentially shedding light on this cosmic conundrum. The implications of solving the Hubble tension are profound. It could reshape our understanding of the universe's evolution, its composition, and even its ultimate fate. As we continue to explore this mystery, one thing is clear: the universe still holds many secrets, and the Hubble tension is a reminder that even our most well-established theories are not immune to challenge. What will we discover next? Only time and the relentless pursuit of knowledge will tell. Now turning to the third of our 25 unsolved questions, we explore a topic that has fascinated scientists and dreamers alike. What is the fate of the universe? The answer to this question hinges on the delicate balance between the forces driving the universe's expansion and the gravitational pull trying to hold it together. Based on our current understanding, there are three primary scenarios that could define the ultimate destiny of the cosmos: the Big Freeze, the Big Crunch, and the Big Rip. Each of these outcomes is deeply tied to the behavior of dark energy and the rate at which the universe is expanding. First, let's consider the Big Freeze, also known as the heat death scenario. In this scenario, the universe continues to expand at an accelerating rate driven by dark energy. Over trillions of years, galaxies will drift farther and farther apart, stars will burn out, and the universe will grow colder and darker. Eventually, all that will remain is a vast, empty expanse devoid of light, heat, or life. This chilling outcome is currently the most widely accepted model, given the observed acceleration of the universe's expansion. Next, we have the Big Crunch, a dramatic reversal of the Big Freeze. In this scenario, the expansion of the universe slows down and eventually stops as gravity overcomes the repulsive force of dark energy. The universe would then begin to collapse in on itself, with galaxies, stars, and even atoms being crushed together in a fiery, cataclysmic event. Some theories suggest that this collapse could trigger another Big Bang, leading to a cyclical universe that expands and contracts endlessly. However, current observations of the universe's accelerating expansion make this scenario less likely, though not entirely impossible. Finally, there's the Big Rip, a more violent and sudden end to the universe. In this scenario, dark energy becomes so dominant that it not only accelerates the expansion of the universe, but also tears apart galaxies, stars, planets, and even atoms themselves. Over time, the fabric of space-time would be ripped apart, leaving behind a universe in complete disarray. While this outcome is speculative, it highlights the profound influence dark energy could have on the universe's fate. The key to understanding these scenarios lies in the nature of dark energy and the precise rate of the universe's expansion. If dark energy remains constant, the Big Freeze seems the most likely outcome. But if dark energy evolves over time, becoming stronger or weaker, the balance could shift, leading to a Big Crunch or a Big Rip. As we continue to study the universe's expansion and refine our measurements, we may one day uncover the clues needed to predict its ultimate fate. Until then, the question remains, which of these cosmic endings awaits us? The answer lies hidden in the mysteries of dark energy and the ever-expanding cosmos. Now turning to the fourth of our 25 unsolved questions, we delve into one of the most profound mysteries of cosmology. Is the universe infinite or finite? This question strikes at the very heart of our understanding of existence, challenging us to grapple with the true nature of the cosmos. For centuries, philosophers and scientists have debated whether the universe stretches on forever or if it has a boundary, and even today, the answer remains elusive. To explore this question, we must first consider the shape of the universe. According to Einstein's theory of general relativity, the universe could be flat, open, or closed, each with implications for its size and ultimate fate. A flat universe suggests an infinite expanse where space extends endlessly in all directions. An open universe shaped like a saddle would also be infinite, but with a curvature that causes parallel lines to diverge over vast distances. A closed universe, on the other hand, would be finite, resembling the surface of a sphere where space curves back on itself. In this scenario, if you traveled far enough in one direction, you might eventually return to your starting point. Observational evidence, particularly from the cosmic microwave background, or CMB, has provided some clues. The CMB is the faint afterglow of the Big Bang, and its patterns reveal the universe's geometry. Measurements from missions like the Planck satellite suggest that the universe is flat to an extraordinary degree of precision. This supports the idea of an infinite universe, but it doesn't entirely rule out the possibility of a finite one. For example, the universe could be finite but so vast that its curvature is undetectable within the observable limits of our instruments. Another piece of the puzzle lies in the concept of the observable universe. Even if the universe is infinite, we can only see a finite portion of it, the part from which light has had time to reach us since the Big Bang. This observable universe spans about 93 billion light-years in diameter, but what lies beyond is a mystery. Could there be more galaxies, more structures, or even entirely different regions of space-time that we cannot see? Or does the universe simply end at some point with nothing beyond? These questions remain unanswered as our current tools and theories cannot probe beyond the observable horizon. The debate over the universe's size and shape is further complicated by the role of dark energy and the universe's expansion. If dark energy continues to drive the expansion at an accelerating rate, it could influence the universe's geometry over time, potentially altering our understanding of its boundaries. Additionally, theories like cosmic inflation suggest that the universe underwent a rapid expansion in its earliest moments, which could have stretched space to such an extent that it appears flat and infinite, even if it is finite on a larger scale. Ultimately, the question of whether the universe is infinite or finite remains unresolved, a testament to the complexity and grandeur of the cosmos. As we continue to refine our observations and develop new theories, we may one day uncover the truth. But for now, the mystery endures, inviting us to ponder the vastness of existence and the limits of our knowledge. What lies beyond the observable universe? Is there an edge, or does space stretch on forever? The answers, like the universe itself, remain just out of reach. Now turning to the fifth of our 25 unsolved questions, we venture into the very beginning of everything: what caused the Big Bang? This question takes us to the edge of our understanding, where science meets the profound mystery of existence itself. The Big Bang is often described as the moment the universe began, but what triggered this colossal event? And what, if anything, existed before it? These are questions that continue to challenge even the most brilliant minds in cosmology. To explore this, let's start with what we know. The Big Bang theory describes how the universe expanded from an incredibly hot and dense state around 13.8 billion years ago. But the theory doesn't explain what caused this expansion or what conditions existed before it. Some scientists suggest that the Big Bang wasn't the true beginning, but rather a transition from a previous state of the universe. This idea opens the door to fascinating possibilities, such as the concept of a cyclic universe, where the Big Bang is just one in an endless series of expansions and contractions. One leading theory involves quantum fluctuations. In the quantum world, particles can spontaneously appear and disappear due to the inherent uncertainty of space-time. Some researchers propose that a quantum fluctuation in a pre-existing void could have triggered the Big Bang, creating the universe as we know it. This idea ties into the concept of a multiverse, where our universe is just one of countless others, each born from its own quantum event. If true, the Big Bang might not be a unique event but part of a much larger cosmic tapestry. Another intriguing possibility is that the Big Bang was the result of a collision between higher dimensional objects such as brains in string theory. According to this idea, our universe exists on a three-dimensional brane, and the Big Bang occurred when two branes collided, releasing an immense amount of energy that set the universe in motion. While this theory is highly speculative, it offers a compelling explanation for the origin of the Big Bang and the nature of the cosmos. Yet, despite these theories, the question of what caused the Big Bang remains unanswered. Our current understanding of physics breaks down at the moment of the Big Bang, making it difficult to probe further. The laws of general relativity and quantum mechanics, which govern the large and small scales of the universe respectively, cannot yet be reconciled at this extreme point. This leaves us with a tantalizing mystery. Was the Big Bang truly the beginning, or is it just one chapter in an infinite cosmic story? As we continue to explore this question, new technologies and theories may bring us closer to the truth. But for now, the origin of the Big Bang remains one of the greatest unsolved mysteries in science, a reminder of how much we still have to learn about the universe and our place within it. What lies beyond the Big Bang? Was there a before, or is time itself a construct that began with the universe? These questions invite us to ponder the very nature of existence and the limits of human understanding. Now turning to the sixth of our 25 unsolved questions, we shift our focus to one of the most elusive and mysterious components of the universe, dark matter. Unlike the stars, planets, and galaxies we can see, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is felt through its gravitational effects on the visible universe. So, what exactly is dark matter, and why does it remain one of the greatest puzzles in modern cosmology? To understand dark matter, let's start with what we do know. Observations of galaxies and galaxy clusters show that they rotate and move in ways that can't be explained by the visible matter alone. There simply isn't enough gravity from stars, gas, and dust to account for the motions we see. This discrepancy led scientists to propose the existence of dark matter, an invisible substance that makes up about 27% of the universe's total mass and energy. Without it, galaxies would fly apart, and the large-scale structure of the universe as we know it wouldn't exist. But what is dark matter made of? This is where the mystery deepens. Despite decades of research, we still don't have a definitive answer. One leading hypothesis is that dark matter consists of weakly interacting massive particles, or WIMP. These hypothetical particles would interact only through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Experiments like those conducted in deep underground laboratories aim to catch these elusive particles, but so far, none have been conclusively observed. Another possibility is that dark matter is made up of actions, extremely light particles predicted by certain extensions of the standard model of particle physics. Actions are even harder to detect than WIMP, but experiments are underway to search for their faint signals. There's also the intriguing idea that dark matter could be composed of primordial black holes, remnants of the early universe that formed shortly after the Big Bang. However, this theory remains speculative as no direct evidence of such black holes has been found. The challenge of detecting dark matter lies in its very nature. It doesn't interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light. This makes it invisible to traditional telescopes and other instruments that rely on light. Instead, scientists rely on indirect methods, such as observing the gravitational effects of dark matter on visible matter, or looking for rare interactions in highly sensitive detectors. Despite these efforts, dark matter continues to evade direct detection, leaving us with more questions than answers. Why does this matter? Dark matter plays a crucial role in the universe's expansion and the formation of cosmic structures. Without it, galaxies wouldn't have formed in the way they did, and the universe would look very different. Understanding dark matter could also shed light on the nature of gravity itself and whether our current theories need to be revised. It's a reminder that the universe is far more complex and mysterious than we often realize. As we continue to search for dark matter, new technologies and experiments may bring us closer to uncovering its secrets. But for now, it remains one of the most profound mysteries in science, a hidden force shaping the cosmos in ways we are only beginning to understand. What is dark matter? How does it interact with the rest of the universe? And what will its discovery reveal about the fundamental nature of reality? These questions drive us to explore the unknown, pushing the boundaries of human knowledge and imagination. Now turning to the seventh of our 25 unsolved questions, we delve into one of the most fascinating and pivotal moments in the history of the universe, cosmic inflation. This theory proposes that in the earliest moments after the Big Bang, the universe underwent an exponential expansion, growing from the size of a subatomic particle to something far larger in a fraction of a second. But what exactly caused this rapid expansion, and how did it come to an end? These questions remain at the heart of modern cosmology. To understand cosmic inflation, let's start with what it explains. The universe we observe today is remarkably uniform on large scales, with galaxies and cosmic structures distributed evenly across the cosmos. This uniformity is puzzling because without inflation, regions of the universe that are now far apart would never have had time to interact and reach the same temperature. Inflation solves this by suggesting that these regions were once close together, allowing them to equilibrate before being rapidly stretched apart. But what triggered inflation in the first place? The leading idea is that it was driven by a hypothetical field called the inflaton field. This field, which permeated the early universe, is thought to have had a unique property. Its energy caused space to expand at an incredible rate. As the inflaton field decayed, its energy was converted into the particles and radiation that filled the young universe, marking the end of inflation and the beginning of the hot Big Bang phase we're more familiar with. However, the details of this process are far from settled. What exactly was the inflaton field? Was it a single field, or were multiple fields involved? And how did it transition from driving rapid expansion to releasing its energy? These are some of the biggest unanswered questions in cosmology. Without a deeper understanding of the inflaton field, we can't fully explain how inflation began or how it ended. Another mystery is what caused inflation to stop. If the inflaton field decayed, what triggered that decay? Some theories suggest that quantum fluctuations played a role, causing the field to lose energy in certain regions and allowing the universe to transition out of inflation. But this is still speculative, and we lack direct evidence to confirm these ideas. The implications of cosmic inflation are profound. Not only does it explain the uniformity of the universe, but it also provides a mechanism for the formation of cosmic structures. Tiny quantum fluctuations during inflation are thought to have been stretched to cosmic scales, seeding the density variations that eventually grew into galaxies and galaxy clusters. This connection between the quantum world and the cosmos is one of the most remarkable aspects of the theory. Yet, despite its successes, inflation remains a theory. While it fits many observations, we still lack direct evidence to confirm it. Future experiments, such as those studying the cosmic microwave background or gravitational waves from the early universe, may provide the clues we need. But for now, cosmic inflation stands as one of the most compelling yet mysterious chapters in the story of our universe. As we continue to explore the origins of the cosmos, the questions surrounding inflation remind us of how much we still have to learn. What triggered this rapid expansion? How did it end? And what does it tell us about the fundamental laws of physics? These questions drive us to probe deeper into the universe's earliest moments, seeking answers that could reshape our understanding of reality itself. Now turning to the eighth of our 25 unsolved questions, we step into a realm that stretches the boundaries of imagination, the possibility of other universes. The idea of a multiverse, where our universe is just one of many, has captivated scientists and thinkers alike. But how does this concept connect to the expansion of our own universe, and could it help us solve some of the mysteries we've already explored? The multiverse theory arises from several areas of physics, including cosmic inflation and quantum mechanics. If inflation occurred in the early universe, as we discussed earlier, it's possible that it didn't happen just once. Instead, inflation could be an ongoing process, creating countless bubble universes that each expand and evolve independently. In this scenario, our universe would be just one bubble in a vast cosmic foam, with other universes existing alongside ours, each with its own unique physical laws and properties. But how does this tie into the expansion of our universe? If inflation is the driving force behind the multiverse, then the same mechanisms that caused our universe to expand could also be responsible for creating other universes. This raises intriguing questions. Are these other universes expanding at the same rate as ours? Could they have different rates of expansion or even different fates? And if they exist, could we ever detect them? Another fascinating aspect of the multiverse idea comes from quantum mechanics. In the quantum world, particles can exist in multiple states simultaneously until they are observed. Some interpretations of quantum mechanics suggest that every possible outcome of a quantum event actually happens, but in separate, parallel universes. This means that for every decision you make, there could be another universe where you made a different choice. While this sounds like science fiction, it's a serious area of study that could have profound implications for our understanding of reality. The multiverse theory also ties into the concept of dark energy, the mysterious force driving the accelerated expansion of our universe. If dark energy behaves differently in other universes, it could mean that some universes expand faster, slower, or even collapse back in on themselves. This variability could help explain why our universe has the specific properties it does, including the precise amount of dark energy needed for life to exist. However, the multiverse remains a highly speculative idea. One of the biggest challenges is that, by definition, other universes would be beyond our observable reach. If they exist, they are likely separated from us by vast stretches of space or even different dimensions, making direct detection nearly impossible. But scientists are exploring indirect ways to test the multiverse hypothesis, such as looking for imprints of collisions between our universe and others in the cosmic microwave background, or searching for anomalies in the distribution of galaxies that could hint at the influence of neighboring universes. The multiverse theory also raises profound philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? And what does that mean for our place in the cosmos? While these questions may seem abstract, they push us to think beyond the limits of our own universe and consider the broader tapestry of existence. As we ponder the possibility of other universes, we're reminded that the expansion of our own universe is just one piece of a much larger puzzle. Whether the multiverse is real or not, the idea challenges us to rethink our understanding of space, time, and reality itself. And as we continue to explore the mysteries of the cosmos, the multiverse remains one of the most tantalizing and thought-provoking concepts in modern science. Now turning to the 9th of our 25 unsolved questions, we delve into a fundamental mystery, the true age of the universe. How old is the cosmos we call home? While scientists have made remarkable progress in estimating the universe's age, conflicting measurements continue to spark debate and raise intriguing questions about our understanding of cosmic history. The most widely accepted estimate places the universe at around 13.8 billion years old. This figure is primarily derived from observations of the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing the patterns and temperature fluctuations in this ancient light, scientists can calculate how long it has taken for the universe to expand and cool to its current state. This method, combined with measurements of the universe's expansion rate, provides a robust framework for determining its age. However, not all measurements align with this estimate. Some studies of the oldest stars in our galaxy, based on their brightness and composition, suggest that the universe might be slightly older, perhaps closer to 14 billion years. These stars, known as globular clusters, are thought to have formed relatively soon after the Big Bang. By studying their properties, astronomers can infer the minimum age required for these stars to have evolved to their current state. Yet, this method introduces its own uncertainties, as it relies on assumptions about stellar evolution and the initial conditions of the early universe. Adding to the complexity, measurements of the universe's expansion rate, known as the Hubble constant, also yield conflicting results. Some techniques, such as observing distant supernova or the cosmic microwave background, suggest a faster expansion rate, which would imply a younger universe. Other methods, like studying the motions of nearby galaxies or the behavior of gravitational lenses, point to a slower expansion rate, hinting at an older universe. This discrepancy, known as the Hubble tension, remains one of the most puzzling challenges in modern cosmology. So, why do these discrepancies persist? One possibility is that our current understanding of the universe's composition and behavior is incomplete. For instance, the properties of dark energy, which drives the accelerated expansion of the universe, might not be as constant as we assume. If dark energy's influence has changed over time, it could affect the expansion rate and consequently our estimates of the universe's age. Similarly, unknown particles or forces in the early universe could have altered the timeline of cosmic evolution, leaving us with conflicting clues. Another factor is the inherent difficulty of measuring cosmic distances and timescales. The universe is vast, and even small errors in our observations can lead to significant discrepancies in our calculations. For example, determining the distance to faraway galaxies or the brightness of ancient stars requires precise calibration and a deep understanding of the underlying physics. Any uncertainties in these measurements can ripple through our calculations, affecting our estimates of the universe's age. Despite these challenges, scientists are making strides in refining their methods and resolving the discrepancies. New telescopes, such as the James Webb Space Telescope, are providing unprecedented views of the early universe, allowing us to peer further back in time than ever before. Meanwhile, advanced simulations and theoretical models are helping us better understand the complex interplay of forces that shape the cosmos. As we continue to explore this question, we're reminded that the universe's age is more than just a number. It's a window into the history and evolution of everything we know. Each conflicting measurement challenges us to refine our understanding and uncover new layers of cosmic truth. And as we piece together the puzzle of the universe's age, we move closer to answering one of the most profound questions of all: how did we get here? Now turning to the 10th of our 25 unsolved questions, we explore a puzzling feature of the cosmos, its remarkable uniformity. Why is the universe so consistent in temperature and density across vast distances? This question lies at the heart of what cosmologists call the horizon problem, and it challenges our understanding of how the universe evolved after the Big Bang. Imagine looking at the cosmic microwave background, the oldest light in the universe. No matter which direction you observe, the temperature of this ancient radiation is almost exactly the same, down to a tiny fraction of a degree. This uniformity is astonishing, especially when you consider that regions of the universe now billions of light years apart were once too far apart to have ever been in contact. According to the laws of physics as we understand them, these regions shouldn't have had enough time to exchange heat or information to reach such a uniform state. So, how did they end up so similar? One of the leading explanations is the theory of cosmic inflation. This idea suggests that in the earliest moments after the Big Bang, the universe underwent an incredibly rapid expansion, doubling in size many times over in just a fraction of a second. This explosive growth would have smoothed out any irregularities, creating the uniform conditions we observe today. Think of it like stretching a wrinkled sheet of paper. once it's pulled taut, the wrinkles disappear, leaving a smooth surface. Inflation could have done something similar for the universe, evening out its temperature and density on a cosmic scale. But while inflation provides a compelling solution, it's not without its challenges. For one, we don't yet know what caused inflation to start or what made it stop. The mechanism behind this rapid expansion remains one of the biggest mysteries in cosmology. Additionally, inflation predicts certain patterns in the cosmic microwave background that we've observed, but it also raises new questions. For example, why did inflation last just long enough to create the uniformity we see, but not so long that the universe became completely featureless? Another possibility is that the universe's uniformity is a result of processes we don't yet understand. Some theories propose that the early universe was filled with exotic particles or fields that interacted in ways we can't yet describe. These interactions might have allowed distant regions to communicate or synchronize in ways that defy our current understanding of physics. Alternatively, the uniformity could be a sign that our universe is just one part of a much larger multiverse, where different regions have different properties, and we happen to live in a particularly uniform patch. The horizon problem also highlights the limits of our observational tools. While we can measure the cosmic microwave background with incredible precision, it's still just a snapshot of the universe at a single moment in time. To fully understand how the universe achieved its uniformity, we need to piece together its entire history from the first moments after the Big Bang to the present day. This requires not only better observations but also new theoretical frameworks that can explain how the universe's large-scale structure emerged from its chaotic beginnings. As we continue to explore this question, we're reminded that the universe's uniformity is more than just a curiosity. It's a clue to the fundamental laws that govern everything we see. Each observation challenges us to refine our theories and uncover new layers of cosmic truth. And as we piece together the puzzle of the horizon problem, we move closer to answering one of the most profound questions of all: how did the universe come to be the way it is? Now turning to the 11th of our 25 unsolved questions, we delve into the fascinating intersection of quantum mechanics and cosmology. What role do the strange and counterintuitive rules of quantum physics play in the universe's expansion? This question takes us into the realm of the very small, where particles behave in ways that defy our everyday intuition, and asks how these tiny phenomena might shape the vast cosmos. At the heart of quantum mechanics is the idea that particles don't have definite properties until they're observed. Instead, they exist in a state of probability, described by what's called a wave function. This uncertainty isn't just a quirk of tiny particles, it's a fundamental feature of reality. And when we apply these principles to the early universe, we start to see how quantum effects might have played a crucial role in shaping the cosmos as we know it. One of the most intriguing ideas is that quantum fluctuations, tiny, random variations in energy, could have been the seeds of cosmic structure. In the earliest moments of the universe, these fluctuations might have been stretched and amplified by the rapid expansion of space during inflation. Over billions of years, these tiny ripples could have grown into the galaxies, clusters, and superclusters we see today. In this way, the quantum world might have left its fingerprints on the largest scales of the universe. But the connection between quantum mechanics and the universe's expansion doesn't stop there. Some theories suggest that quantum effects could still be influencing the cosmos today. For example, the mysterious force driving the universe's accelerated expansion, dark energy, might have a quantum origin. One possibility is that dark energy is related to the energy of empty space itself, a concept known as vacuum energy. According to quantum mechanics, even a perfect vacuum isn't truly empty. Instead, it's teeming with virtual particles that pop in and out of existence, creating a background energy that could be driving the universe apart. However, this idea comes with its own set of challenges. When physicists try to calculate the amount of vacuum energy predicted by quantum mechanics, they get a number that's astronomically larger than what we observe in the universe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. It suggests that our understanding of quantum mechanics and its connection to the cosmos is still incomplete. Another area where quantum mechanics might play a role is in the behavior of black holes. These incredibly dense objects are thought to warp space and time so severely that even light can't escape their grasp. But when we apply quantum principles to black holes, we find that they might not be as simple as they seem. For instance, quantum effects could cause black holes to slowly lose mass over time, a process known as Hawking radiation. This raises the question of whether black holes and the way they interact with the universe could have an impact on the overall expansion of space. As we explore the role of quantum mechanics in the universe's expansion, we're reminded of how deeply interconnected the smallest and largest scales of reality truly are. The same rules that govern the behavior of particles in a lab might also shape the fate of the entire cosmos. And while many questions remain, each discovery brings us closer to understanding how the quantum world and the universe's expansion are intertwined. This journey into the quantum realm challenges us to rethink our assumptions and opens up new possibilities for uncovering the secrets of the cosmos. Now turning to the 12th of our 25 unsolved questions, we shift our focus to the enigmatic role of black holes in the universe's expansion. These cosmic giants, born from the collapse of massive stars, are not just fascinating objects in their own right, they might also hold clues to how the universe grows and evolves over time. But do black holes help drive the expansion of space, or do they work against it? This question takes us into the heart of one of the most mysterious aspects of cosmology. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. Their immense gravitational pull warps the fabric of space and time, creating effects that ripple across the cosmos. But how does this influence the universe's expansion? One possibility is that black holes could act as cosmic anchors, slowing down the rate at which space expands. Their gravity pulls matter together, counteracting the outward push of dark energy. In this view, black holes might be seen as a balancing force, helping to regulate the pace of the universe's growth. However, the story doesn't end there. Some theories suggest that black holes could actually contribute to the expansion of the universe. For example, as black holes consume matter and energy, they release radiation and jets of particles into space. These energetic processes could, in theory, add to the overall energy content of the universe, potentially influencing its expansion. Additionally, the way black holes interact with dark energy, the mysterious force driving accelerated expansion, remains an open question. Could black holes somehow amplify or modify the effects of dark energy, or do they simply coexist with it, playing a more passive role? Another intriguing idea is that black holes might be connected to the universe's expansion through their role in galaxy formation. Galaxies often have supermassive black holes at their centers, and these black holes are thought to play a key role in shaping the galaxies around them. As galaxies grow and evolve, their black holes could influence the distribution of matter and energy on large scales, indirectly affecting the universe's expansion. This raises the possibility that black holes are not just local phenomena but integral players in the cosmic dance of expansion. But perhaps the most mind-bending connection between black holes and the universe's expansion comes from the realm of quantum mechanics. As we discussed earlier, black holes are thought to emit Hawking radiation, a quantum effect that causes them to slowly lose mass over time. This process could have implications for the universe's expansion, as the energy released by black holes might contribute to the overall dynamics of space. Some researchers even speculate that black holes could be linked to the nature of dark energy itself, though this remains a highly speculative and unresolved idea. As we explore the role of black holes in the universe's expansion, we're reminded of how interconnected the cosmos truly is. From the smallest quantum effects to the largest structures in the universe, everything seems to be part of a grand, intricate web. Black holes, with their immense gravity and mysterious properties, are a key piece of this puzzle. And while many questions remain, each discovery brings us closer to understanding how these cosmic giants shape the fate of the universe. This journey into the heart of black holes challenges us to rethink our assumptions and opens up new possibilities for uncovering the secrets of the cosmos. Now turning to the 13th of our 25 unsolved questions, we delve into the significance of the cosmological constant, a concept that has puzzled scientists for over a century. Introduced by Albert Einstein in his theory of general relativity, the cosmological constant was initially proposed as a way to balance the equations and describe a static universe, one that neither expands nor contracts. At the time, the prevailing belief was that the universe was unchanging, and Einstein added this constant to ensure his equations reflected that idea. However, when Edwin Hubble discovered that the universe was actually expanding, Einstein famously called the cosmological constant his greatest blunder. Yet, in a surprising twist, modern cosmology has brought this constant back into the spotlight, revealing its potential role in the universe's accelerated expansion. So, what exactly is the cosmological constant? In simple terms, it represents a form of energy that permeates all of space, acting as a kind of repulsive force that counteracts gravity. This energy is thought to be responsible for the observed acceleration of the universe's expansion, a phenomenon attributed to dark energy. In fact, the cosmological constant is often considered the simplest explanation for dark energy, providing a mathematical framework to describe its effects. But here's the catch: despite its importance, the value of the cosmological constant remains one of the biggest mysteries in physics. Why does it have the specific value it does? And why is this value so finely tuned to allow the existence of galaxies, stars, and ultimately, life? The cosmological constant's value is so small that it defies our current understanding of physics. According to quantum field theory, the energy of empty space known as vacuum energy should be vastly larger than what we observe. This discrepancy, known as the cosmological constant problem, suggests that there's something fundamental we're missing about the nature of space and time. Some scientists propose that the constant's value might be the result of a deeper, yet-to-be-discovered principle, while others speculate that it could be a random outcome of the multiverse, where different regions of space have different values. Either way, the cosmological constant challenges our understanding of the universe on both the largest and smallest scales. Another intriguing aspect of the cosmological constant is its relationship with the fate of the universe. If it remains constant over time, as its name suggests, it will continue to drive the universe's accelerated expansion, leading to a future where galaxies drift apart and the cosmos grows colder and darker, a scenario known as the Big Freeze. However, if the cosmological constant isn't truly constant and changes over time, it could lead to entirely different outcomes, such as a big rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. This uncertainty underscores just how much we still have to learn about this mysterious force. The cosmological constant also raises profound questions about the nature of reality itself. Why does the universe seem so finely tuned to allow the existence of complex structures? Is this a coincidence, or is there a deeper reason behind it? Some theorists suggest that the constant's value might be linked to the fundamental laws of physics, while others argue that it could be evidence of a multiverse where our universe is just one of many, each with its own set of physical constants. These ideas push the boundaries of our understanding and challenge us to rethink the very foundations of cosmology. As we explore the significance of the cosmological constant, we're reminded of how much we still have to uncover about the universe. From its role in the accelerated expansion of space to its connection with dark energy and the fate of the cosmos, this constant is a key piece of the puzzle. And while its true nature remains elusive, each discovery brings us closer to unraveling one of the greatest mysteries in science. This journey into the heart of the cosmological constant invites us to question our assumptions and opens up new possibilities for understanding the universe's deepest secrets. Now turning to the 14th of our 25 unsolved questions, we explore the intriguing possibility of hidden dimensions and their potential impact on the universe's expansion and structure. For centuries, we've understood space as having three dimensions: length, width, and height, with time serving as the fourth dimension in the fabric of space-time. But what if there are more dimensions lurking beyond our perception? This idea, once confined to the realm of science fiction, has become a serious topic of study in modern physics, offering new ways to explain some of the universe's deepest mysteries. The concept of extra dimensions arises from theories like string theory, which suggests that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. For these strings to work mathematically, they require more than the 4 dimensions we're familiar with. Some versions of the theory propose as many as 10 or even 11 dimensions. These extra dimensions are thought to be compactified or curled up at such small scales that they're invisible to us. But if they exist, they could hold the key to understanding phenomena like gravity's weakness compared to other forces, or even the nature of dark energy and the universe's expansion. One of the most fascinating implications of hidden dimensions is their potential influence on gravity. In our three-dimensional world, gravity follows the inverse square law, meaning its strength decreases with the square of the distance. But if extra dimensions exist, gravity could spread into these dimensions, weakening its effect in our observable universe. This could explain why gravity is so much weaker than the other fundamental forces, like electromagnetism. Some theories even suggest that dark energy, the mysterious force driving the universe's accelerated expansion, could be a manifestation of gravity leaking into these hidden dimensions. Hidden dimensions might also play a role in the universe's large-scale structure. For instance, they could affect how galaxies and galaxy clusters form and evolve over time. If gravity behaves differently on cosmic scales due to these extra dimensions, it could alter the way matter clumps together, potentially explaining some of the anomalies we observe in the distribution of galaxies. Additionally, these dimensions could influence the rate of the universe's expansion, offering an alternative explanation for the acceleration we attribute to dark energy. But how do we test for the existence of hidden dimensions? One approach involves looking for tiny deviations in the behavior of gravity at extremely small scales. Experiments using highly sensitive instruments like torsion balances or particle accelerators aim to detect signs of extra dimensions by measuring forces between objects at microscopic distances. Another method involves studying cosmic phenomena, such as the cosmic microwave background or gravitational waves, for subtle clues that might hint at the presence of these dimensions. The idea of hidden dimensions also ties into broader questions about the nature of reality. If extra dimensions exist, what do they look like and how do they interact with our familiar 4-dimensional world? Are they uniform or do they vary in shape and size across the universe? And if we could perceive them, how would that change our understanding of space, time, and the cosmos as a whole? These questions challenge us to think beyond the limits of our everyday experience and consider possibilities that could revolutionize our understanding of the universe. As we ponder the existence of hidden dimensions, we're reminded of how much remains unknown about the fabric of reality. From their potential influence on gravity and dark energy to their role in shaping the universe's structure, these dimensions could hold answers to some of the most profound questions in cosmology. While their existence is still speculative, The search for hidden dimensions pushes the boundaries of science and invites us to imagine a universe far more complex and mysterious than we ever thought possible. Now turning to the 15th of our 25 unsolved questions, we delve into the origin of cosmic structures and their connection to the universe's expansion. Galaxies, galaxy clusters, and superclusters are the building blocks of the cosmos, forming a vast web of matter that stretches across the universe. But how did these structures come to be, and what role does the universe's expansion play in their formation and evolution? The story of cosmic structures begins shortly after the Big Bang, when the universe was a hot, dense soup of particles and energy. Tiny fluctuations in density caused by quantum fluctuations served as the seeds for future structures. As the universe expanded and cooled, gravity began to pull matter together, amplifying these initial irregularities. Over billions of years, regions with slightly higher density attracted more matter, eventually collapsing into the first stars, galaxies, and larger structures we see today. One of the key factors in this process is dark matter, an invisible substance that makes up about 27% of the universe's total mass and energy. Dark matter's gravitational pull played a crucial role in shaping the cosmic web, providing the scaffolding upon which ordinary matter could gather and form galaxies. Without dark matter, the universe would lack the necessary gravitational framework to create the intricate structures we observe. The distribution of these structures is not random but follows a pattern known as the cosmic web. This web consists of dense filaments of galaxies and gas, separated by vast, empty regions called cosmic voids. The filaments intersect at nodes where galaxy clusters and superclusters reside. This large-scale structure is a direct result of the universe's expansion, which stretched and shaped the distribution of matter over time. But the relationship between cosmic structures and the universe's expansion is not one-sided. As galaxies and clusters form, their gravitational pull can influence the rate of expansion in their local regions. For example, dense clusters can slow down expansion in their vicinity, while voids with their lower density allow expansion to proceed more rapidly. This interplay between gravity and expansion is a delicate balance that continues to shape the cosmos. One of the biggest mysteries surrounding cosmic structures is why they appear so uniform on large scales. Observations of the cosmic microwave background, the afterglow of the Big Bang, reveal a remarkably even distribution of temperature and density in the early universe. Yet, over time, this uniformity gave way to the complex web of structures we see today. Understanding how this transition occurred is a major challenge for cosmologists. Theories like cosmic inflation attempt to explain this uniformity by proposing that the universe underwent a rapid expansion in its earliest moments, smoothing out irregularities and setting the stage for structure formation. However, questions remain about how inflation ended and how the initial quantum fluctuations evolved into the cosmic structures we observe. Additionally, the role of dark energy, the mysterious force driving the universe's accelerated expansion, adds another layer of complexity to this puzzle. As we study the origin of cosmic structures, we gain insights into the fundamental forces and processes that govern the universe. From the role of dark matter and dark energy to the influence of gravity and expansion, these structures are a testament to the intricate interplay of cosmic forces. Yet many questions remain unanswered. How did the first galaxies form, and why do they cluster in the patterns we observe? What role do cosmic voids play in the overall structure of the universe? And how will the continued expansion of the universe affect the evolution of these structures in the distant future? The search for answers to these questions drives some of the most ambitious projects in modern astronomy, from mapping the distribution of galaxies across the universe to simulating the formation of cosmic structures in supercomputers. Each discovery brings us closer to understanding the origins of the cosmic web and its connection to the universe's expansion. As we explore these mysteries, we are reminded of the profound complexity and beauty of the cosmos and the endless possibilities that lie ahead in our quest to unravel its secrets. Now turning to the 16th of our 25 unsolved questions, we delve deeper into the mystery of why the universe's expansion is accelerating. This phenomenon, first discovered in the late 1990s through observations of distant supernovae, has fundamentally reshaped our understanding of the cosmos. Instead of slowing down due to gravity, as scientists once expected, the universe is expanding at an ever-increasing rate. But what is driving this acceleration, and what does it mean for the future of the cosmos? The leading explanation for this accelerated expansion is dark energy, a mysterious form of energy that permeates all of space. Dark energy is thought to make up about 68% of the universe's total energy content, dwarfing the contributions of both ordinary matter and dark matter. Unlike gravity, which pulls matter together, dark energy exerts a repulsive force that pushes space apart. This repulsion is what causes the universe's expansion to speed up over time. But what exactly is dark energy? The simplest and most widely accepted model describes it as a property of space itself, known as the cosmological constant. Proposed by Albert Einstein over a century ago, the cosmological constant represents a constant energy density filling empty space. While Einstein initially introduced it to maintain a static universe, it was later abandoned when the expansion of the universe was discovered. Now it has been revived as a possible explanation for dark energy. However, the cosmological constant raises its own set of questions. Why does it have the specific value it does, and why is it so finely tuned to allow for the existence of galaxies, stars, and life? Alternative theories have also been proposed to explain the universe's accelerating expansion. One such idea is quintessence, a dynamic form of dark energy that changes over time. Unlike the cosmological constant, which remains constant, quintessence could vary in strength and density, potentially offering a more nuanced explanation for the observed acceleration. Another possibility is that our understanding of gravity is incomplete. Modifications to Einstein's theory of general relativity, such as theories involving extra dimensions or new fields, could account for the accelerated expansion without invoking dark energy at all. The implications of the universe's accelerating expansion are profound. If dark energy continues to dominate, the universe could face a future known as the Big Rip, where galaxies, stars, and even atoms are torn apart as the expansion becomes unstoppable. Alternatively, dark energy's influence could weaken over time, leading to a more gradual expansion. Understanding the nature of dark energy is crucial not only for predicting the universe's fate, but also for unraveling the fundamental laws of physics. Efforts to study dark energy and the universe's accelerating expansion are ongoing. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map the distribution of galaxies and measure the rate of expansion with unprecedented precision. These observations could provide clues about the nature of dark energy and help distinguish between competing theories. As we explore this mystery, we are reminded of how much we still have to learn about the cosmos. The accelerating expansion of the universe challenges our understanding of space, time, and energy, pushing the boundaries of science and imagination. What drives this acceleration, and how will it shape the future of the universe? These questions remain at the forefront of cosmology, inspiring new discoveries and deepening our appreciation for the vast, dynamic universe we call home. Now turning to the 17th of our 25 unsolved questions, we explore the role of neutrinos in the universe's expansion. Often referred to as ghost particles, neutrinos are among the most elusive and mysterious particles in the cosmos. They are incredibly lightweight, electrically neutral, and interact with matter so weakly that they can pass through entire planets without being detected. Yet, despite their ghostly nature, neutrinos play a significant role in shaping the universe as we know it. neutrinos were first proposed in the 1930s to explain a puzzling observation in radioactive decay. Since then, they have been detected in various cosmic processes, from nuclear reactions in the Sun to the explosive deaths of massive stars. But how do these ghostly particles influence the universe's expansion? To answer this, we need to look back to the early universe just moments after the Big Bang. In the first few seconds after the Big Bang, the universe was a seething soup of particles and energy. Neutrinos were among the most abundant particles in this primordial mix, outnumbering even protons and electrons. As the universe expanded and cooled, neutrinos decoupled from other matter, traveling freely through space. Their immense numbers and high energy meant they contributed significantly to the total energy density of the early universe, influencing its expansion rate. Even today, neutrinos continue to play a subtle but important role in cosmic evolution. While they are no longer as dominant as they were in the early universe, their presence affects the distribution of matter on large scales. Neutrinos, with their tiny but non-zero mass, contribute to the overall gravitational pull of the universe. This influence, though small, can impact the formation of cosmic structures like galaxies and galaxy clusters, which in turn affects the universe's expansion. One of the most intriguing aspects of neutrinos is their potential connection to dark energy. Some theories suggest that neutrinos could interact with dark energy in ways we don't yet understand. For example, if neutrinos have a property called neutrino mass hierarchy, it could provide clues about the nature of dark energy and its role in the universe's accelerating expansion. Alternatively, neutrinos might be part of a larger family of particles that influence cosmic expansion in ways we have yet to discover. Efforts to study neutrinos and their role in the universe are ongoing. Experiments like the IceCube Neutrino Observatory in Antarctica and the upcoming Deep Underground Neutrino Experiment aim to detect neutrinos from cosmic sources and measure their properties with unprecedented precision. These studies could shed light on how neutrinos contribute to the universe's expansion and whether they hold the key to solving some of cosmology's biggest mysteries. As we continue to probe the universe's secrets, neutrinos remind us of the intricate connections between the smallest particles and the largest structures in the cosmos. Their ghostly presence challenges our understanding of physics and inspires new questions about the forces that shape our universe. What role do neutrinos play in the universe's expansion, and how might they help us unravel the mysteries of dark energy and cosmic evolution? These questions drive scientists to push the boundaries of knowledge, bringing us closer to understanding the vast, dynamic universe we call home. Now turning to the 18th of our 25 unsolved questions, we delve into the mysteries of gravity on cosmic scales. Gravity, the force that binds planets, stars, and galaxies together, is one of the most fundamental forces in the universe. Yet, when we look at the vast expanse of the cosmos, gravity behaves in ways that challenge our understanding, raising questions about whether Einstein's theory of general relativity is the complete picture. Einstein's theory of general relativity, formulated over a century ago, has been incredibly successful in explaining the behavior of gravity on scales ranging from falling apples to orbiting planets. It describes gravity not as a force in the traditional sense, but as the curvature of space-time caused by mass and energy. This revolutionary idea has passed countless tests, from predicting the bending of light around massive objects to explaining the precise orbits of planets. However, when we apply general relativity to the entire universe, some puzzling discrepancies emerge. One of the most significant challenges is explaining the universe's accelerated expansion. According to general relativity, the gravitational pull of all the matter in the universe should slow down the expansion over time. Yet, observations show that the expansion is speeding up, driven by an unknown force we call dark energy. This discrepancy has led scientists to question whether general relativity needs to be modified or extended to account for this unexpected behavior. Another area where general relativity faces challenges is on the largest cosmic scales. When we observe the distribution of galaxies and galaxy clusters, we find that gravity alone, as described by general relativity, cannot fully explain their movements. There appears to be more gravitational pull than what visible matter can account for, leading to the hypothesis of dark matter. While dark matter provides a plausible explanation, its nature remains one of the greatest mysteries in physics, and some scientists wonder if modifying our understanding of gravity could eliminate the need for dark matter altogether. Several alternative theories have been proposed to address these issues. For example, modified Newtonian dynamics, or MUND, suggests that gravity behaves differently on large scales than it does on smaller ones. Another approach involves adding extra dimensions to spacetime, as suggested by string theory, which could alter how gravity operates on cosmic scales. While these ideas are intriguing, they have yet to be confirmed by observational evidence, leaving the question of gravity's true nature unresolved. Efforts to test the limits of general relativity and explore alternative theories are ongoing. Experiments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have detected gravitational waves, ripples in spacetime caused by cataclysmic events like merging black holes. These observations provide new ways to test general relativity in extreme conditions. Meanwhile, missions like the European Space Agency's Euclid telescope aim to map the distribution of dark matter and dark energy, offering insights into how gravity operates on the largest scales. As we continue to explore the cosmos, the question of how gravity works on cosmic scales remains a central puzzle in modern physics. Does general relativity need to be revised, or are we missing something fundamental about the nature of the universe? The answers to these questions could reshape our understanding of gravity, dark energy, and the very fabric of spacetime itself. With each new discovery, we move closer to unraveling the mysteries of the universe's expansion and the forces that govern it. Now turning to the 19th of our 25 unsolved questions, we explore the ultimate fate of dark energy and its profound implications for the universe. Dark energy, the mysterious force driving the accelerated expansion of the cosmos, has been a central focus of modern cosmology since its discovery in the late 1990s. But as much as we've learned about its effects, one question looms large: what will happen to dark energy over time, and how will it shape the destiny of the universe? Currently, the most widely accepted model of dark energy is the cosmological constant, a term introduced by Einstein and later revived to explain the universe's accelerated expansion. In this model, dark energy is a constant force, unchanging over time and uniformly distributed throughout space. If this is true, the universe will continue to expand at an accelerating rate, leading to a scenario known as the Big Freeze. In this distant future, galaxies will drift farther and farther apart, stars will burn out, and the cosmos will become a cold, dark, and empty place. However, not all scientists are convinced that dark energy is constant. Some theories suggest that dark energy could evolve over time, either growing stronger or weaker. If dark energy increases in strength, it could lead to a far more dramatic fate for the universe, the Big Rip. In this scenario, the repulsive force of dark energy would eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a whimper but with a catastrophic rupture of spacetime. On the other hand, if dark energy weakens over time, the universe's expansion could slow down, potentially leading to a big crunch. In this scenario, gravity would eventually regain dominance, pulling everything back together in a reverse of the Big Bang. The universe would collapse into an infinitely dense point, possibly setting the stage for a new cycle of cosmic birth and death. While this idea is intriguing, there is currently no observational evidence to support it. The challenge in determining the fate of dark energy lies in our limited understanding of its nature. Is it truly a constant force, or does it vary over time? To answer this, scientists are studying the expansion rate of the universe with unprecedented precision. Projects like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope aim to measure how dark energy has influenced the universe's expansion over billions of years. By comparing these observations to theoretical models, researchers hope to uncover clues about dark energy's behavior and its ultimate destiny. The question of dark energy's fate is not just an academic exercise, it has profound implications for the future of the cosmos. Will the universe continue to expand forever, growing colder and darker, or will it meet a more dramatic end, torn apart or crushed back into a singularity? The answers to these questions could reshape our understanding of the universe's evolution and the forces that govern it. As we peer deeper into the cosmos, the mystery of dark energy remains one of the most compelling challenges in modern science, reminding us that the universe is full of surprises waiting to be uncovered. Now turning to the 20th of our 25 unsolved questions, we delve into the observational limits of the universe's expansion and the challenges scientists face in studying this cosmic phenomenon. As we peer deeper into the cosmos, one question arises: are there boundaries to what we can observe, and will we ever reach a point where the universe's expansion becomes impossible to measure? The universe's expansion is primarily observed through the redshift of distant galaxies, a phenomenon where light from these galaxies stretches as space itself expands. This redshift provides crucial data about how fast the universe is growing and how that rate has changed over time. However, as we look farther out into space, we're also looking back in time, and this creates significant challenges. The farther away an object is, the fainter and more difficult it becomes to observe. At some point, the light from these distant galaxies may become so faint that it's undetectable, even with the most advanced telescopes. Another limitation comes from the nature of the universe itself. The expansion of space means that some regions of the cosmos are moving away from us faster than the speed of light. While this doesn't violate the laws of physics, since it's space itself that's expanding, not the objects moving through it, it does mean that light from these regions will never reach us. This creates a boundary known as the cosmological horizon, beyond which we cannot see. It's like trying to observe a ship that sailed beyond the horizon. No matter how powerful your telescope, some parts of the universe will always remain hidden. Adding to these challenges is the fact that the universe's expansion is accelerating, driven by dark energy. As the expansion speeds up, the distance between galaxies increases, and the light they emit becomes stretched into longer, redder wavelengths. Over time, this could make it increasingly difficult to detect the light from distant galaxies, as it shifts into the infrared and eventually into wavelengths that are beyond the capabilities of our current instruments. This raises the question, will there come a time when the universe's expansion outpaces our ability to observe it? Despite these challenges, scientists are continually pushing the boundaries of what we can see. Projects like the James Webb Space Telescope are designed to observe the faintest, most distant objects in the universe, probing the early stages of cosmic history. Future missions, such as the Nancy Grace Roman Space Telescope, aim to map the universe's expansion with unprecedented precision, potentially revealing new insights into dark energy and the limits of our observational capabilities. The question of observational limits is not just about technology, it's about the fundamental nature of the universe. Are there regions of the cosmos that will forever remain beyond our reach? Or will advancements in technology and our understanding of physics allow us to peer even further into the depths of space? As we continue to explore these questions, we're reminded that the universe is vast, mysterious, and full of surprises, challenging us to push the boundaries of what we know and what we can see. Now turning to the 21st of our 25 unsolved questions, we explore the intriguing connection between the universe's expansion and entropy, a concept rooted in the second law of thermodynamics. At first glance, these two ideas might seem unrelated. One deals with the stretching of space itself, while the other describes the tendency of systems to move toward disorder. But as we dig deeper, we find that these forces may be more intertwined than we realize. Entropy, often described as the measure of disorder in a system, is a fundamental principle of thermodynamics. The second law states that in any closed system, entropy always increases over time. This means that energy tends to spread out and systems naturally move toward a state of equilibrium. But how does this apply to the universe as a whole? The universe is, in many ways, the ultimate closed system, and its expansion raises fascinating questions about how entropy evolves on a cosmic scale. One of the key ideas here is that the universe's expansion might influence the way entropy increases. As space stretches, the volume of the universe grows, and this could provide more room for entropy to spread out. Some scientists suggest that the expansion of the universe could be driving the increase in entropy, creating a direct link between these two phenomena. If this is true, it would mean that the universe's expansion isn't just a geometric process, it's also a thermodynamic one, shaping the way energy and matter are distributed across the cosmos. But the relationship between expansion and entropy isn't straightforward. For example, as the universe expands, galaxies and other structures move farther apart, reducing the density of matter. This could, in theory, slow down certain processes that contribute to entropy, such as the collisions and interactions between particles. At the same time, the cooling of the universe as it expands might also affect how entropy evolves. These complexities make it difficult to pin down exactly how expansion and entropy are connected, and whether one is driving the other. Another layer to this mystery is the role of dark energy. As the force behind the universe's accelerating expansion, dark energy could be influencing the way entropy changes over time. If dark energy continues to dominate, it might push the universe toward a state of maximum entropy, often referred to as the heat death of the universe. In this scenario, the universe would become so vast and diffuse that no usable energy would remain, and all processes would grind to a halt. But is this the inevitable fate of the cosmos, or are there other possibilities? The connection between expansion and entropy also ties into broader questions about the arrow of time. Why does time move forward, and why do we remember the past but not the future? Some physicists believe that the increase in entropy is what gives time its direction. If that's the case, then understanding how entropy and expansion are linked could shed light on the very nature of time itself. As we continue to explore this relationship, we're reminded that the universe is a complex, interconnected system, where even the most fundamental forces are deeply intertwined. The question of how expansion and entropy influence each other is not just a scientific puzzle, it's a window into the very fabric of reality. And as we push the boundaries of our understanding, we may uncover new insights that reshape our view of the cosmos and our place within it. Now turning to the 22nd of our 25 unsolved questions, we delve into the role of cosmic voids, those vast, seemingly empty regions of space, and how they influence the universe's expansion. These voids, which can span hundreds of millions of light years, are not just empty spaces but play a crucial role in shaping the large-scale structure of the cosmos. But how exactly do these enormous gaps affect the way the universe expands? Cosmic voids are regions where the density of matter is significantly lower than the surrounding areas. They are surrounded by filaments and walls of galaxies, creating a web-like structure known as the cosmic web. While these voids might appear empty, they are not entirely devoid of matter. Instead, they contain sparse distributions of gas, dark matter, and the occasional galaxy. What makes them fascinating is their impact on the universe's expansion. One of the key ways cosmic voids influence expansion is through their gravitational effects. In regions with higher matter density, such as galaxy clusters, gravity is stronger, pulling matter together and slowing down the local expansion of space. In contrast, the weaker gravitational pull within voids allows space to expand more freely. This means that voids act as accelerators of cosmic expansion, contributing to the overall rate at which the universe grows. But the relationship between voids and expansion isn't one-sided. As the universe expands, voids themselves grow larger. Over time, matter continues to flow out of these regions, drawn toward the denser structures surrounding them. This process, known as void growth, further enhances the expansion within the voids, creating a feedback loop where expansion and void growth reinforce each other. Another intriguing aspect of cosmic voids is their potential connection to dark energy. Some theories suggest that the behavior of voids could provide clues about the nature of dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy behaves differently in low-density regions, studying voids might help us understand its properties and how it interacts with the fabric of space-time. However, cosmic voids also present challenges for astronomers. Because they contain so little matter, they are difficult to observe directly. Instead, scientists often study them indirectly by analyzing the distribution of galaxies and the way light bends as it passes through these regions. These observations help us map the structure of voids and understand their role in the universe's expansion. The study of cosmic voids also ties into broader questions about the universe's evolution. How did these vast, empty regions form in the first place? Are they a natural consequence of the universe's initial conditions, or do they result from specific processes during cosmic evolution? Answering these questions could provide deeper insights into the forces that have shaped the cosmos over billions of years. As we explore the influence of cosmic voids on the universe's expansion, we're reminded once again of the intricate balance between matter, space, and time. These seemingly empty regions are far from insignificant. They are key players in the grand story of the cosmos, and as we continue to study them, we may uncover new pieces of the puzzle that help us understand the universe's past, present, and future. Now turning to the 23rd of our 25 unsolved questions, we explore the role of time in the universe's expansion. Time, as we experience it, seems linear and unchanging, but when we consider the vast scales of the cosmos, its nature becomes far more mysterious. Could the expansion of the universe influence the very fabric of time itself? And does time have a beginning or an end? To understand this, we need to revisit the concept of space-time, the four-dimensional framework that combines the three dimensions of space with the dimension of time. According to Einstein's theory of general relativity, space and time are not separate entities but are interwoven, forming a single continuum. This means that as space expands, time may also be affected in ways we are only beginning to comprehend. One of the most intriguing ideas is that the expansion of the universe could stretch time itself. Just as galaxies move away from each other as space expands, the passage of time might also stretch in an expanding universe. This could mean that time flows differently in different regions of the cosmos, depending on the local rate of expansion. For example, in regions where space is expanding rapidly, time might appear to slow down relative to regions where expansion is slower. But what does this mean for the beginning and end of time? The Big Bang theory suggests that the universe began as an infinitely dense and hot singularity, marking the start of both space and time. If time began with the Big Bang, does that mean it could also end? Some theories propose that if the universe continues to expand indefinitely, time might stretch to a point where it effectively runs out, leading to a state where change ceases to occur. This idea is closely tied to the concept of the Big Freeze, one of the possible fates of the universe. On the other hand, if the universe were to collapse in a big crunch, time might reverse its flow, leading to a scenario where the end of the universe mirrors its beginning. This raises profound questions about the nature of time. Is it a one-way street, or could it loop back on itself under certain conditions? Another fascinating aspect is the relationship between time and dark energy. If dark energy is driving the accelerated expansion of the universe, could it also be influencing the flow of time? Some scientists speculate that dark energy might cause time to dilate or accelerate in ways we don't yet understand, adding another layer of complexity to this cosmic puzzle. As we ponder the role of time in the universe's expansion, we are reminded of how deeply interconnected space, time, and matter truly are. These questions challenge our understanding of reality and push the boundaries of what we know about the cosmos. And while we may not have all the answers yet, each discovery brings us closer to unraveling the mysteries of time and its place in the grand tapestry of the universe. Now turning to the 24th of our 25 unsolved questions, we delve into the mystery of redshift and whether it might have explanations beyond the Doppler effect. Redshift, the phenomenon where light from distant galaxies appears to stretch toward longer, redder wavelengths, has long been a cornerstone of our understanding of the universe's expansion. But could there be other factors at play that mimic this effect? The Doppler effect, which explains how the wavelength of light changes as objects move away from us, is the most widely accepted explanation for redshift. As galaxies move apart due to the expansion of space, their light stretches, shifting toward the red end of the spectrum. This observation has been a key piece of evidence supporting the Big Bang theory and the idea of an expanding universe. However, some scientists have proposed alternative explanations that challenge this conventional view. One such alternative is the idea of tired light, a hypothesis suggesting that light loses energy as it travels through space, causing its wavelength to stretch over time. Proponents of this theory argue that the redshift we observe might not be due to the motion of galaxies, but rather to some unknown interaction between light and the fabric of space itself. While this idea has been largely dismissed due to a lack of supporting evidence, it remains an intriguing possibility that continues to spark debate. Another alternative explanation involves the influence of gravity on light. According to Einstein's theory of general relativity, massive objects can warp space-time, bending the path of light and altering its wavelength. This effect, known as gravitational redshift, has been observed in light passing near massive objects like black holes. Could gravitational redshift on a cosmic scale contribute to the redshift we see in distant galaxies? While this idea is theoretically possible, it would require an extraordinary distribution of mass in the universe to produce the observed effects, making it an unlikely primary explanation. There's also the possibility that our understanding of the fundamental properties of light and space is incomplete. Could there be unknown forces or interactions at play that affect how light travels through the cosmos? Some researchers have explored the idea that the expansion of space itself might not be uniform, leading to variations in redshift that don't align with the Doppler effect. Others have suggested that quantum effects or hidden dimensions might influence the behavior of light in ways we don't yet understand. As we explore these alternative explanations, it's important to remember that the Doppler effect remains the most robust and widely supported explanation for redshift. However, the existence of these alternatives highlights the importance of questioning our assumptions and remaining open to new ideas. After all, some of the greatest discoveries in science have come from challenging the status quo. The mystery of redshift reminds us that even the most well-established theories can have gaps waiting to be filled. As we continue to study the universe, each observation and experiment brings us closer to understanding whether redshift is purely a result of the Doppler effect or if there's more to the story. And with that, we move forward to our final question, which takes us to the very edge of what we can observe and imagine. Now turning to the 25th and final question in our exploration of the universe's expansion, we venture into the unknown, what lies beyond the observable universe. This question takes us to the very edge of what we can see, measure, and even imagine, pushing the boundaries of our understanding to their absolute limits. The observable universe is the portion of the cosmos that we can detect from Earth, limited by the distance light has had time to travel since the Big Bang. This boundary, often referred to as the cosmic horizon, stretches about 93 billion light-years across. But what lies beyond this horizon? Is there more universe out there, or does it simply end? The truth is, we don't know and may never know for certain. One possibility is that the universe is infinite, stretching endlessly in all directions. If this is the case, then what we call the observable universe is just a tiny fraction of a much larger, perhaps limitless cosmos. In an infinite universe, there could be regions so far away that their light will never reach us, no matter how long we wait. These regions would remain forever hidden, their mysteries locked beyond our cosmic horizon. Another idea is that the universe is finite but unbounded, much like the surface of a sphere. If you were to travel in one direction long enough, you might eventually loop back to your starting point. In this scenario, the universe could have a finite size, but without any edges or boundaries. However, this raises the question of what lies outside this finite universe, a concept that is difficult to grasp and even harder to test. Some theories suggest that our universe is just one of many in a vast multiverse. In this view, what lies beyond the observable universe could be other universes, each with its own unique laws of physics and properties. These parallel universes might be separated by unimaginable distances or exist in dimensions beyond our perception. While the multiverse theory is fascinating, it remains speculative as there is currently no way to observe or confirm the existence of other universes. There's also the possibility that the universe is expanding faster than the speed of light in some regions, meaning that those areas are forever receding from our view. This expansion could create regions of space that are causally disconnected from us, meaning no information or light from those regions could ever reach us. These areas would remain eternally beyond our reach, shrouded in mystery. As we ponder what lies beyond the observable universe, we're reminded of the profound limitations of our current knowledge and technology. The cosmic horizon is not just a physical boundary, it's a reminder of how much we have yet to discover. Every observation, every experiment, and every theory brings us closer to understanding the true nature of the cosmos, but some questions may remain unanswered for generations to come. This final question encapsulates the essence of our journey through these 25 unsolved mysteries. It challenges us to think beyond what we know, to imagine the unimaginable, and to remain curious in the face of the unknown. And with that, we conclude our exploration, but the quest for answers continues, as vast and endless as the universe itself. Now turning to the role of technology in solving these cosmic mysteries, we find ourselves at the forefront of human ingenuity. The questions we've explored about dark energy, the universe's expansion, and what lies beyond the observable universe are not just philosophical musings. They are challenges that scientists are actively working to unravel, and technology is their most powerful tool. One of the most significant advancements has been in the field of telescopes. From the Hubble Space Telescope to the James Webb Space Telescope, these instruments have allowed us to peer deeper into the cosmos than ever before. The James Webb Telescope, for instance, is designed to observe the earliest galaxies, giving us a glimpse into the universe's infancy. By studying the light from these ancient stars, scientists hope to uncover clues about the universe's expansion and the nature of dark energy. Particle accelerators like the Large Hadron Collider are another critical piece of the puzzle. These massive machines allow physicists to recreate conditions similar to those just after the Big Bang. By smashing particles together at incredible speeds, researchers can study the fundamental forces and particles that make up the universe. This research could shed light on the nature of dark matter, the behavior of neutrinos, and even the origins of cosmic inflation. Computational models have also revolutionized our ability to understand the cosmos. Supercomputers can simulate the universe's evolution, from the Big Bang to the formation of galaxies and the large-scale structure we see today. These simulations help scientists test theories about dark energy, the universe's expansion, and the fate of the cosmos. By comparing these models with observational data, researchers can refine their understanding and identify areas where new theories are needed. But technology isn't just about building bigger and better instruments, it's also about collaboration. Projects like the Event Horizon Telescope, which captured the first image of a black hole, rely on a global network of telescopes working together. This kind of international cooperation allows scientists to pool resources, share data, and tackle questions that no single country or institution could solve alone. As we look to the future, new technologies promise to push the boundaries even further. Missions like the Nancy Grace Roman Space Telescope aim to map the universe in unprecedented detail, while next-generation particle accelerators could reveal new particles and forces. Advances in artificial intelligence and machine learning are also transforming how we analyze data, making it possible to sift through vast amounts of information and uncover patterns that might otherwise go unnoticed. The role of technology in solving these mysteries cannot be overstated. It is the bridge between our questions and the answers we seek, the tool that allows us to explore the cosmos and push the limits of our understanding. As we continue to innovate and collaborate, we move closer to unraveling the secrets of the universe, one discovery at a time. Now turning to the philosophical implications of an expanding universe, we find ourselves grappling with questions that go beyond the realm of science and into the very nature of existence itself. The idea that the universe is not static but constantly growing challenges our most fundamental assumptions about reality, time, and our place in the cosmos. For centuries, humans have viewed the universe as a stable, unchanging backdrop to our lives, but the discovery of cosmic expansion has shattered that notion. If the universe is expanding, what does that mean for the concept of time? Is time itself stretching along with the cosmos, and if so, does time have a beginning or an end? These questions force us to rethink our understanding of time as a linear, unchanging force and consider it as something more dynamic and intertwined with the fabric of the universe. The expansion of the universe also raises profound questions about existence. If the universe is growing, what lies beyond its boundaries? Is there a limit to how far it can expand, or will it continue to stretch indefinitely? These questions challenge our perception of reality, pushing us to consider whether the universe is finite or infinite, and what that means for the nature of existence itself. Are we part of a larger multiverse, or is our universe all there is? The answers to these questions could redefine our understanding of reality and our place within it. Moreover, the concept of an expanding universe forces us to confront the impermanence of everything we know. Stars, galaxies, and even the fabric of space itself are in a constant state of change. This impermanence challenges our desire for stability and permanence, reminding us that everything in the cosmos is part of a larger, ever-evolving process. It invites us to reflect on the fleeting nature of our own existence and the legacy we leave behind in a universe that is always in motion. But perhaps the most profound philosophical implication of an expanding universe is the way it reshapes our understanding of meaning and purpose. If the universe is constantly growing, does that mean it has a goal or direction, or is it simply expanding without any inherent purpose? These questions touch on the very essence of what it means to be human, forcing us to grapple with the idea that the universe may not have a predetermined destiny, and that meaning is something we create rather than something we discover. As we ponder these questions, we are reminded that the universe's expansion is not just a scientific phenomenon, but a philosophical one as well. It challenges us to think deeply about the nature of reality, the passage of time, and our place in the cosmos. And as we continue to explore these mysteries, we may find that the answers lie not just in the stars, but within ourselves. Now turning to the future of cosmology, we find ourselves on the brink of groundbreaking discoveries that could reshape our understanding of the universe's expansion. Scientists and researchers around the world are preparing for a new era of exploration, armed with advanced technology and innovative theories that promise to shed light on the mysteries we've been discussing. One of the most exciting developments on the horizon is the launch of next-generation space telescopes, such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission. These powerful instruments are designed to map the universe in unprecedented detail, allowing us to study dark energy and the large-scale structure of the cosmos with greater precision than ever before. By observing how galaxies are distributed and how their light is distorted by dark matter, these missions could provide crucial insights into the forces driving the universe's accelerated expansion. On the ground, experiments like the Vera-C, Rubin Observatory's legacy survey of space and time are set to revolutionize our understanding of cosmic evolution. This ambitious project will capture images of billions of galaxies, tracking their movements over time and helping us measure the expansion rate of the universe with remarkable accuracy. Combined with data from space telescopes, these observations could finally resolve the Hubble tension, the discrepancy between different measurements of the universe's expansion rate, and bring us closer to understanding the true nature of dark energy. Meanwhile, particle physicists are pushing the boundaries of our knowledge with experiments like those at the Large Hadron Collider. By recreating the conditions of the early universe, these experiments aim to uncover new particles or forces that could explain the behavior of dark matter and dark energy. Theories like supersymmetry and string theory are also being tested, offering potential explanations for the fundamental nature of the cosmos and its expansion. In addition to these technological advancements, new theoretical frameworks are emerging that challenge our current understanding of the universe. Some scientists are exploring the possibility that dark energy is not a constant force but one that changes over time, while others are investigating whether modifications to Einstein's theory of general relativity could account for the universe's accelerated expansion. These ideas, though still in their early stages, could lead to paradigm-shifting discoveries that redefine our understanding of the cosmos. As we look to the future, it's clear that the quest to unravel the mysteries of the universe's expansion is far from over. With each new mission, experiment, and theory, we move one step closer to answering the profound questions that have puzzled us for decades. And as we continue to explore the cosmos, we are reminded that the journey of discovery is as important as the destination, a journey that promises to reveal not just the secrets of the universe, but also our place within it. Now turning to the conclusion of our exploration, we've journeyed through 25 of the most profound unsolved questions about the universe's expansion, questions that challenge our understanding of space, time, and the very fabric of reality. From the enigmatic nature of dark energy to the mysteries of cosmic inflation, from the fate of the universe to the possibility of hidden dimensions, each question reminds us how much we still have to learn about the cosmos. These mysteries are not just scientific puzzles, they are windows into the fundamental nature of existence itself, inviting us to keep asking, keep exploring, and keep pushing the boundaries of what we know. The significance of these questions cannot be overstated. They shape the future of cosmology, driving the development of cutting-edge technology, groundbreaking experiments, and revolutionary theories. They remind us that the universe is a vast, dynamic, and ever-evolving place, full of wonders waiting to be discovered. And while we may not have all the answers yet, the pursuit of these questions is what propels us forward, inspiring new generations of scientists, thinkers, and dreamers to look up at the stars and wonder. As we wrap up this journey, I encourage you to stay curious. The mysteries of the universe are not just for scientists, they belong to all of us. Whether you're a seasoned space enthusiast or just beginning to explore the wonders of the cosmos, there's always more to discover. Share your thoughts in the comments below. What question fascinates you the most? What do you think lies beyond the observable universe? Let's keep the conversation going. And if you enjoyed this deep dive into the mysteries of the universe, don't forget to subscribe and hit the notification bell so you never miss out on more space-related content. Together, let's continue to explore the unknown, unravel the mysteries of the cosmos, and celebrate the endless wonder of the universe. Thank you for joining me on this journey, and remember, the stars are just the beginning.